Hello to anybody watching this video. Today I am going to be doing my capstone presentation over difference equations, one-dimensional mapping, and chaos. My name is Timothy Cobb, and this is my first time recording something over Zoom, so let's hope it goes well. To start off, we're going to be looking at the sequence of numbers 1, 1, 2, 3, 5, 8, 13, 21, 34, so on and so forth. I'm sure most of the people watching this are math majors. I'm pretty sure we've all encountered this before. This is the Fibonacci sequence, which is a recursive relation. A recursive relation is defined as any kth term can be found by combining the terms before it. Specifically for the Fibonacci sequence, you find the kth term by adding the k minus 1th term and the k minus 2th term. What I'm going to be diving into, difference equations, are somewhat similar to recursive relations, but they differ in a couple of ways. So we're going to look into the definition of a difference equation. A difference equation is a mathematical equality involving the differences between successive values of a function of a discrete variable. So to better understand this, we need to understand what a discrete variable is. And a discrete variable is defined as a variable that is defined of or of interest only for values that differ by some finite amount, usually a constant and often 1. So a difference equation can be expressed in the terms of delta y sub n equals y sub n plus 1 minus y sub n. The more interesting difference equations can be expressed in terms of y sub n equals some function of y sub n's before it. And we're going to be looking into an example later where your y sub nth term can be found by taking the cosine of the term before it. We're also going to be looking at one-dimensional maps. And so just to get that definition off right off the bat, a one-dimensional map is defined as a function where each term in a function can be found with the difference of other terms of the function, i.e. a function that takes the form xn plus 1 equals some function of xn. And a point within a one-dimensional map is a fixed point if f of x equals x. So we're going to consider the function f of x equals cosine x, where our initial condition is 0. And so then our first term, f1, is going to equal cosine of 0, which is 1. We can then compute more and more terms of this function. So to compute our second term, f sub 2, we would take cosine of 1 and get 0.543. To get our ninth term, f sub 9, we would take the cosine of 0.7221 and get 0.7504. And you can see that these numbers start to oscillate around 0.7391. And at the 24th term, we finally get a repeat. We go from 0.7391 to 0.7391. That means that 0.7391 is a fixed value of our function cosine. We're next going to be looking into cobwebbing. And cobwebbing is a mapping scheme that can be used to show how a function behaves over time. To perform cobwebbing, we first plot the line y equals x, and then we plot the line of our function. So in the earlier example, we would then plot the function cosine. And it's important to note that often with cobwebbing, we only do it on the interval from 0 to 1. And so we wouldn't be looking at cosine in its entirety all the way to infinity. We would just be looking at it on the interval 0 to 1. The next step is to plot the continuous function of our iterative map. And we do this by placing our first point in our iterative map, x naught and f of x sub naught. We then draw a horizontal line to the diagonal line at point fx naught, fx naught. And we then plot a vertical line to the continuous curve at point fx naught, fx naught. And we then repeat this process for each iteration step. And this is a really wordy explanation, and it's much easier to see in an example and pictures. And so we're going to be diving into an example that allows us to do just that. So we're going to look at the function f of x equals 3x times 1 minus x. We then begin our process for performing cobwebbing by plotting the line y equals x, which we can see in our picture below, and also the function f of x equals 3x times 1 minus x. We will then choose our initial condition of x naught equals 0.1, and we then calculate the value of x at fx naught and attain the value of 0.27. And so we plot that initial vertical line that travels from 0.10 to 0.1.27. And we can see this in the picture below. And we then draw a line perpendicular to the line we just drew. And in that line segment, when we hit our y equals x line, we can also get this line by plotting the line from 0.1.27 to 0.27.27. We then go about constructing our next vertical line and plot it. And we continue iterating this process until we arrive at a cobweb plot that looks something like this. Now we can see that our function begins to cycle. It begins to shrink in on side itself around the point 0.2 or 2/3, or 0.6 repeating, 0.6 repeating, which is where these two graphs intersect, y equals x and 3x times 1 minus x. Thus, our function is cyclic and it has a fixed point that it approaches asymptotically at 2/3, 2/3. Just because 3x with 1 minus x and the initial condition of 0.1 is cyclic doesn't mean that every function similar to 3x times 1 minus x is that. We can guess how some functions behave, but this isn't true for all functions. When a function behaves in a way that is harder for us to understand, we call it chaotic. And here's an example of a chaos cobweb plot. So instead of having f of x equals 3x times 1 minus x, we have f of x equals 3.75x times 1 minus x with x naught equals 2.2, and we receive a cobweb plot that looks something like this. We can quickly see that there's no point that we begin to cycle around, which is an immediate red flag, but we also see large bands where it is completely filled in with red. And each of those bands shows an infinite number of steps where we're barely changing in value, which means that we can have a variety of points that we're approaching for a very long time, which means that our function is chaotic. And so a more formal definition of chaos is when chaos occurs in a system, when a deterministic system exhibits aperiodic behavior that depends sensitively on the initial conditions, thereby rendering long-term prediction impossible. And so to better understand chaos, we need to understand sensitivity to initial conditions. The function fx has sensitivity to initial conditions if there exists a delta greater than 0, such that for any x and any open set n, there exists a y in n and an n greater than or equal to 0, such that the distance between f and x and f and y is greater than delta. To further understand chaos, we're going to be looking at the tint function. And the tint function is defined as 2x if x is less than or equal to 1/2. And the tint function is then defined as 2 times 1 minus x if x is greater than or equal to 1/2. And so this is what the tint function looks like on the interval 0, 1. And we can see that it's somewhat similar to our earlier example of 3x 1 minus x, but it's not smooth. It's meets at a jagged point. And so to further understand chaos and how to rigorously prove it, we need to have a bookkeeping tool called an itinerary. An itinerary is a bookkeeping device that assigns a discrete value to different intervals of a graph. So here in this picture below, we can see the itinerary of the tint function. And to further understand what an itinerary does, we need to understand what an orbit is. An orbit of a initial condition is the numbers or the sequence that follows from that initial condition. So in our cosine example, our orbit of our initial condition of 0 were those 24 numbers, and then it ended with repeating 0.7391. And what an itinerary does is it looks at where each element of the orbit lies within the interval that your function is on, and then it places a discrete variable, either L or R, to it. And so when we look at an itinerary, we can see how a function behaves over a long period of time quite quickly. So we're going to be diving into an example of an itinerary. So we're going to consider the tint function on the interval 0 to 1, and we'll assign the discrete symbol L to the subinterval of 0, 1, 0, 1 half. We will assign the discrete symbol R to the subinterval of 0, 1, 1 half, 1. We then consider the initial condition x0 equals 5/6. So we can see right off the bat that 5/6 belongs to the subinterval 1 half, 1. And so the itinerary of x0 equals 5/6 begins with the symbol R. We then consider the second term in the orbit of x0, which we can compute by taking x sub 1 equals, and then we put 5/6 into our tint function. So we compute 2 times 1 minus 5/6 equals 1/3. This value belongs to the subinterval 0, 1 half, and so the second term in the itinerary of x0 equals 5/6 is an L. So the itinerary of x0 equals 5/6 begins our L. We then continue this process as far as we like to explore where the different elements of the orbit of x0 equals 5/6 lay within our function. So we're going to be looking at the theorem that the tint function is chaotic on the interval 0, 1, and we're going to be looking at how to rigorously prove this. So to start our proof, the idea of it is we're going to start with two initial conditions that are extremely close to each other, so close that they have the same itinerary up to the kth point. We're then going to see that after that kth point in their orbit, they can separate and end up with itineraries and points that are quite far away from each other, thus showing sensitivity to initial conditions. So we're going to consider the tint function on the interval 0, 1. We want to show that our function is chaotic. We'll be using our bookkeeping tool, the itinerary, to perform this proof. So we're going to consider the itinerary T1 to Tk, where each T sub I equals L or T sub I equals R. So for example, our itinerary could be L K times, or it could be R K times, or it could be any combination of the two. The important thing is that it is the same up to that kth point. And we're first going to note that we have 2 to the k choices for our itinerary, as we're choosing between L or R at each term in our itinerary. And it's also important to note that we can see that each of our subintervals gets quite small as k gets large, because we're stuck within that interval 0, 1, and the sum of our subintervals cannot exceed our initial interval. So essentially, as we keep on breaking up our interval into more and more little pieces, these little pieces are getting extremely small. And so our itinerary, T1 to Tk, for a large k, will contain subintervals corresponding to the itineraries T1 to Tk followed by an LL, T1 to Tk followed by an LR, T1 to Tk followed by an RL, and T1 to Tk followed by an RR. So this idea hinges on the fact that each of our itineraries further breaks up our subintervals into smaller and smaller subintervals. And we're going to note that each subinterval of our function has length equal to 1/2 to the k. Essentially, as we take more and more steps in our itinerary, we're halving how long our subintervals are. And so if we choose one point from each of our above subintervals, we'll have 4 initial conditions within 1/2 of the k plus 2 of each other, as they all originate within this itinerary t1 to tk. However, we can realize that the ending of the itinerary can result in steps of our orbits at least delta equals 1/4 apart, as a point with the ending itinerary of LL is at least 1/4 away from a point with the ending itinerary RR. So essentially, we have 4 initial conditions, one that ends with the itinerary ending in LL, one that has the itinerary ending in LR, one with the itinerary ending in RL, and one with the itinerary ending in RR. And these all start out extremely close to each other. So close, in fact, that it's 1/2 to the k plus 2 of each other, but they end up 1/4 away. This shows sensitivity to initial conditions, and thus our function is chaotic. So to conclude, we're going to look into some of the different ways that chaos and difference equations have different uses in many different fields. For example, in economics or in business, computing the interest based on prior years is a difference equation. Another example is if we're looking at population growth over a period of time, a difference equation can be used to show that as well. And then chaos is quite interesting to mathematicians because it takes functions that we initially thought we knew a lot about and how they would behave, and shows that perhaps they don't behave as we think they would. And so by beginning to understand this subject via this presentation, in the future, we can delve into some of the other applications of this field of mathematics. Here are my references, and I'd just like to close this up by thanking my advisor, Dr. Quinn, and also Dr. Ryan for teaching the capstone course, and all of my classmates within the capstone course for helping me so much with edits, etc. Thank you for watching my presentation, and I hope you enjoyed it.